So now we have already discussed the definition of Taylor series and the very basic concept of Taylor series. Let's try to answer some illustrative problems. So for the first problem, approximate the function y is equal to sine of x by using a Taylor series expansion about the point x is equal to 0 using 4 terms. Calculate the approximate value of the function at x is equal to pi over 3. So we're given the information to evaluate or approximate the function y is equal to sine of x using 4 terms only about the point x is equal to 0 and approximate value of the function at x is equal to pi over 3. So for this problem, I'll be discussing this one in 3 different approaches or 3 different methods or ways on to solve this problem. So first one is using the manual computation or using our formula. So recall that our formula is equal to f of x is equal to f of p plus f prime p times x minus p, so on and so forth. So take note, using 4 terms, you will need up to the third derivative of y is equal to sine of x and evaluating all of them at the arbitrary point p is equal to 0. Okay, so now first we have our function here, y is equal to sine of x, and evaluating them at the arbitrary point p is equal to 0, sine of 0 is equal to 0. So the first derivative of this one is cosine x. So y prime 0, so substitute cosine 0, it gives us 1. So y double prime negative sine x. So y double prime of 0 or sine of 0 is equal to 0 or negative sine of 0. So y triple prime, so negative cosine x. So y triple prime or a negative cosine of 0, that is equal to negative 1. So now we were able to satisfy the requirement here wherein it was mentioned here that using 4 terms only. So substitute these values into the Taylor series. So this is our our general equation here. Okay, for Taylor series expansion. Now we will arrive with this expression here. Okay. So our first term here, that is 0. So f of p, so that is 0. Okay, as we can see here, that is 0. So plus f prime p times x minus p. So that is just 1, as we can see here, times x minus 0 plus 1 half times 0 times x minus 0 squared plus 1 over 3 factorial times negative 1 times x minus 0 raised to 3. Okay, so now we're ready to simplify this term. So we will arrive with this expression here, x minus x cubed all over 6, and now substituting the value of pi over 3. Okay, as mentioned in this problem, at x equal to pi over 3, so that will be pi over 3 minus pi over 3 quantity cube all over 6. We will arrive with an answer of 0.85580078116. Okay, if you will be double checking it with your calculator, make sure that your calculator is in rad mode or radian mode. Okay, so try to plug it in your calculator. Okay, so definitely we will arrive with that answer 0.85580078116. Okay, but we can check the actual value of sine pi over 3 using our calculator as well. Okay, so sine pi over 3, so the actual value of that function is actually 0.8660254 as shown in this portion. Okay, so meaning to say, after 4 terms of expanding our function, or after using Taylor series expansion, we haven't reached yet the actual value of the function. Okay, so that justifies the definition that a fewer number of terms expanded will not give us a more accurate answer. Okay, so if you want to arrive with a more accurate answer, we must provide at least a greater number of expansion. Okay, but for the sake of this problem, as mentioned in this problem, use 4 terms only. Okay, so with that, we were already able to satisfy the requirement here. So this answer here is already accepted. Okay, so now so we're done with the manual computation. Let's try to solve this using Matlab and using MS Excel. But before we do that, allow me first to discuss the derivation of Taylor series expansion of sine of x. So again, our function is y is equal to sine of x. Thus, substituting it to the general equation of our Taylor series, we arrive with this expression here, okay? And recall that on the previous slide, we were already able to obtain these derivatives here, no? So, these derivatives here, nakuha na natin siya from the previous slides. Okay? So, our goal here is to substitute these derivatives in this equation here. Okay? So, y sub 0, that is 0, so we don't need to write it anymore. Y prime 0, so that is 1. Okay? 1 here, times x all over 1 factorial. Then y double prime of 0, that is 0. We don't need to write it anymore. Y triple prime 0, that is negative 1. So we have negative sign here. So 1 all over 3 factorial. You have 3 factorial times x cubed. Okay, as shown in our general equation. Then going back, y raised to 4. So that is 0. We don't need to write it anymore. Then y raised to 5. So that is 1. So positive sign. So 1 here. Then x raised to 5 all over 5 factorial. Then y raised to 6, again that is 0. Then y raised to 7, negative 1 times x raised to 7 over 7 factorial plus so on and so forth. So we can perform this up to n times, no? So even up to y raised to 100, no? So we can easily perform that. Now, how we can simplify this expression here? Notice that our x's here are in terms of, or their powers here, or exponents are in odd numbers. So we have 1, 3, 5, 7, but they are in increment of 2. And notice that our denominator is just similar with the exponent of x. So they are in odd numbers as well. Okay? So now, simplifying this expression here, we will arrive with this expression here. Okay? So summation of negative 1 raised to n plus 1 times x raised to 2n minus 1 all over 2n minus 1 factorial from n is equal to 1 after up to infinity. Okay? So how did we arrive with this one? So negative 1, if we try to plug it in our calculator, no? Negative 1 raised to 1 plus 1, it will give us what? It will give us just simply positive 1. Okay? So as we can notice here, so we must obtain a positive 1 here. So our n here is with an n value of 1. So since our exponent here are in odd numbers, so with an increment of 2, so we can express that in 2n. But again, 2n will give us an even number. So 2n minus 1 will give us an odd number. So whatever is in the exponent of our x, or the power of x, that will be just the denominator in factorial form, as we can notice in this expression. Okay, so whatever is the value, or whatever is the requirement for the Taylor series expansion of sine x, we could easily evaluate that one using this expression here. Okay, now let's try to solve our previous example, y is equal to sine of x, using Matlab. Okay, so the following codes must be encoded in the Matlab command window. So if we'll be just simply encoding these codes, no, as we can see in this slide, again, we could easily obtain our desired answer. Let me just first discuss the following codes here. Okay, so first we have to identify our function here. Okay, so that is y is equal to sine of x. So Matlab has a special tool for Taylor series expansion. So that is just Taylor 4 equal to Taylor times y. Order means here and 4, meaning to say I'll be expanding my Taylor expansion up to 4th order. Okay, Taylor 8 meaning to say up to 8th order, Taylor 10 up to 10th order. So let's just see what's the difference between these three different expansion of sine x. Okay, so for us to have a better picture of our expansion, so let's just encode it here, 3t Taylor, quantity Taylor 4. Okay, so after encoding these codes, you'll have this answer here. Okay, so as we can notice, no, what we obtained a while ago is x, or was x minus x cubed over 6. Okay, so again, this is after 4 terms only. Okay, so after 4 terms, again, we were not able to achieve the accurate answer of 0.866, no? So that is let's just recap. That is just or that is 0.866025438. Okay, so now let's try to substitute pi over 3, okay, because it was mentioned there that x is equal to pi over 3 to this expansion here, no? So let's check if we will arrive with the answer of 0.866025438. Okay, so let's try to plug it in our calculator. Okay, so let's try to solve it. So for you to easily solve this, try to store pi over 3 in your calculator so that it won't take too much time for you to solve this. Okay, so the answer for this expansion is 0.866025445. I hope you have the same answer. Okay, or I hope you got this answer as well. Okay, so let me just discuss this expansion. As you can notice, what we did on the derivation, we noticed that on each order, there's an alternating in our sign. So it justified the expansion here in Matlab. So positive, negative, then positive here. And at the same time, odd number is the exponent of our x's here. No? So again, it justify the derivations that we did a while ago. Okay, so for us to have a better picture of this expansion, let's try to plot it in Matlab. Okay, so just simply type these codes, no? So plot Taylor 4, that is our first expansion, Taylor 8, Taylor 10, and y here is the true value of our function. Okay, so y here will give us the true value of our function. So let's just provide the limits of our x from -4 to 4, and let's put legend for us to have to easily appreciate the graph. Okay, so after encoding these codes, we will produce this graph here. No, so try to substitute, no, this value here and expect that you will have the same value here